Now that we've spent a lot of time looking at how to find limits of functions in various ways, like from graphs or tables or analytically, we're going to look more in depth at the relationship between limits and whether or not a function is continuous at a point. We've already talked about the fact that these are related concepts, but we're really going to dive deep into this today. Earlier in the year in pre-calc, you looked at the idea of whether or not a function was continuous, and you looked at different types of discontinuity like jumps or holes or asymptotes. And this always, I think, seems a little bit ambiguous in pre-calc because you don't have a hard and fast definition to adhere to, especially when you're trying to decide what type of discontinuity you have. And the reason that there's never a hard and fast definition in pre-calc is because the definition of what it means to be continuous at a point includes calculus and it includes limits. So this is the definition that we're going to look at. The formal definition of the continuity of a function at a point is that a function is continuous at a point x equals c if three things are true. One, the first condition is that at that x equals c, the limit has to exist. And we know that that means a couple things. First, it means that both the limit from the right and from the left have to be finite, so not infinity or negative infinity, and those two one-sided limits have to be equal to each other, so like they both have to be 4. Furthermore, so that's just the definition of a limit that we've seen. To be continuous, the y value, or f of c, needs to be the exact same thing as that limit. We made a big deal when we were talking about limits, how limits don't, the actual y value at x equals c doesn't matter for a limit. For continuity, it does. You need to think about that there has to be a y value there. It can't just be a whole. And the third thing, where those two things come together, you have to have a limit, you have to have a y value, and they have to be the same thing. So the way that I like to think about this is kind of the idea of a bridge going over a river. So here you have my extra artistic river with some green grass on each side, and the brown thing is supposed to be a pre-existing road that leads up to one side of the river. If you wanted to build a functioning bridge over this river, what you would have to do is build the bridge on the other side of the river. You'd have to build the bridge on the other side of the river so that it was going to match up in the same exact place. So it'd have to come together. And that would be like the idea of having a limit at that location. So the left and the right-sided limits have to be the same. If you wanted to be able to get over the river, you'd have to make sure that you built your bridge. You'd actually have to have a bridge. So now I'm going to build an extra artistic purple footbridge right over here, if you like it. And so not only do you have to have a bridge, that's like the y value, the location of the bridge matters. So to make this work, the bridge has to be exactly where the two roads or the limit come together. Some of you might know that last year they built that new pedestrian bridge over the Providence River, and it has an extra weird shape because when they were building it, they actually didn't come the right way from both sides, so it wasn't going to meet in the middle. They had a continuity problem. So this has a lot of real life, very tangible applications. But again, from a calculus point of view, we're looking for there to be a limit. So there's a road on each side. There's got to be a bridge. There has to be f of c has to exist. And the limit and f of c have to be in the same place. So we're going from, in limits, we don't care about the y value. For continuity, we do care about the y value. There has to be one, and it has to be in the right place. So the way we can use this is to talk a little bit more about those three types of discontinuity from pre-calc. You should hopefully remember the idea of a hole, a jump, or a vertical asymptote, which is also referred to as an infinite discontinuity. And in calculus terms, these three discontinuities are actually split up into two further categories. A hole is called a removable discontinuity. And so there are two types of holes. One is where there's an open circle and there's no y value. The other one is an open circle with a y value in a different place, the second picture that I have drawn. And you can see the reason that they refer to this in calculus as removable is if we were to move that one point, either put one in if it was missing or move it down to plug in that hole, we would be able to remove that discontinuity. That would be like the idea of making sure we put the bridge in the right place. The jump discontinuity is the one where basically if you think about the bridge, the roads are heading to the wrong place. So they're never going to meet up. And that's called non-removable because no matter where the bridge is, the y value, you would never be able to have a functioning bridge because the roads are in the wrong spot. And I drew 3 different ways that can look. You can have the closed circle on one side of the jump. You can have no closed circle, so the bridge cannot exist. Or you could have like the 2 roads in different places with a closed circle in a third place, which would be really, really bad. And third, we have the also non-removable infinite discontinuity, and that's a vertical asymptote. So that would be like the 2 roads never even go to the river, and there might not be a bridge. It still counts, by the way, as an infinite discontinuity in the second picture that I drew, which is one side seems totally fine. It's like this would be a piecewise function where the function is going to x equals c, there's a closed circle right there, but then the other side of the piecewise function has an asymptote, and so that still counts as an infinite discontinuity. The way to really tell the difference between these types, especially on a graph, because sometimes especially the difference between a hole and a jump can be a little bit confusing, is to really apply the definition rigorously. So I've done this here. A hole is going to be any x equals c where you can say that the limit exists. So the two sides come together. You didn't have that language in pre-calc, so that was a little bit tricky. So a hole is going to be where the limit exists. A jump is going to be where there is no limit. So at x equals c, there isn't a limit, but the one-sided limits exist. So both of the sides are coming to finite locations. And an infinite discontinuity or vertical asymptote is going to be a place where the limit at x equals c doesn't exist, similar to a jump, but at least one of the one-sided limits also doesn't exist. So you have an going to infinity or negative infinity on one side of that place. So this limit definition for continuity gives us a really hard and fast way to tell the difference between the three types, and that'll be something that'll be useful to us going forward. So the next thing I want to do is show you a couple of examples of the type of question that you might see, particularly in calculus, having to do with continuity and discontinuity. A lot of functions that you'll see involved with continuity will be piecewise functions because in life, things that model real life situations typically are piecewise because it's difficult to model one scenario with just one function. Sometimes you need one function over a certain period of time and then another function over another period of time. And that's where piecewise functions can really come into play. So for these piecewise functions, we're going to look at, are they continuous always? If not, where are they not continuous? What type of discontinuity is it? And I'm going to justify using some elements of that definition. The big thing you want to know about piecewise functions is that the candidates for discontinuity are going to be the breakpoints between the two parts or three parts, depending on how big a piecewise function it is. We're going to be looking; those are going to be your suspicious candidates. On the piecewise function, like on one particular section, you're probably not going to see discontinuity. So, for example, in part A, I can tell that the place that I'd be looking for discontinuity is going to be x equals 1 because that's the break between the two functions. And just looking at this function, I can tell that it's not going to be continuous at 1 right away because it's not defined at 1. So if you don't have a y value at x equals 1, there's no way for it to be continuous. But what we don't know is whether it is a removable discontinuity, aka a hole, or if it's non-removable, a jump or a vertical asymptote. And to do that, what we need to do is look at whether there is a limit at 1 or if there's not a limit at 1. So what I'm going to do is for this idea of justifying, I'm going to check out what my limits are from the right and from the left. And so to find my limit, that is way too big. Let me try that again. To find my limit as x approaches 1 from the right of g of x, I'm going to use my top function because that's where x is greater than 1. And that's going to be negative 1 squared or negative 1. And then I'm going to see what's going on with my limit as x approaches 1 from the left side. And that's going to be using the bottom line where the values are less than 1. And that's going to be 6 minus 5 times 1, or 1. So this is showing me that the right and the left-hand limits they're both finite, but they're not the same, which means this is going to be a jump discontinuity because the two pieces are going to be coming at each other like that. So I'm going to say that we have a jump at x equals 1, since there are a few ways that you could write it that would work, but a great way to do this is just to show that the left and right-sided limits are different. So I'm going to say the limit as x approaches 1 from the right does not equal the limit as x approaches 1 from the left of g of x. So the next thing I'm going to do is I'm going to look at this other piecewise function, and this is a different type of piecewise function. It's the type where you have one function for almost everywhere, the x squared, and then a different function at just one place. And so at x equals 0, this function we're saying is equal to 1. So in this case, it might be continuous at x equals 0 because it is defined at x equals 0, but we need to figure out if the limit at 0 is equal to the function value. So we know that f of 1 is 0. And I didn't say, by the way, what f of 1 was in A because I knew that it was undefined, and so I knew that it was definitely not continuous. So then I just jumped right to the limits to see what type it was. In this case, we do have a possible continuity because at least we have a y value. And then what I need to do is see what my limit is. So my limit as x approaches 0 of f of x is going to be whatever the top line is, because everywhere on both the left and the right, this function is going to be whatever the x squared is. And so the limit of x squared as x approaches 0 is just going to be 0 squared, and so that's 0. Oh, and you know what? I'm so sorry. I'm just realizing I wrote this backwards here. F of 0 is 1, not the other way around. So what this is showing us is that the y value is 1, but the limit is 0. So that means that because the y value and the limit are not the same, that means not continuous. But since we do have a limit, that's telling us that this is going to be a jump discontinuity, which you can probably visualize by thinking about this graph. So what I'm going to say is that we have a hole at x equals 0, since, can't spell since, since the limit as x approaches 0 of f of x exists, but it is not equal to f of 0. And so that makes it a hole or a or a removable discontinuity, which we could remove if we change that second line to make the value at 0 be 0. Another really typical type of AP problem is to give you a piecewise function and put a variable constant in it and find the value that makes the function continuous. So in this case, we've got a piecewise function that breaks at 1, and we want to make sure that we pick an A value that is going to make the function continuous. So since this is a 2-part piecewise function, to be continuous, we basically want, when the pieces come together, we want them to come at the same place. So when, just make this a little bit bigger, what we want is when x equals 1, we want x squared plus x plus a to be equal to x cubed. And so all we need to do here is plug in x equals 1. So say 1 squared plus 1 plus a equals 1 cubed. And so that means that a plus 2 has to equal 1, and a has to be negative 1. And we've succeeded in finding the value that will work. If we graphed this, I promise, I'm not going to do it for the sake of time, but these functions would come together as long as a was negative 1. If a was something else, they wouldn't. This last problem is a similar version of that. We have this piecewise function is the setup where we have one function everywhere except one value and then another value at another place. So this piecewise function, the top line, the x squared minus 16 over x minus 4, the reason that this is defined everywhere except x equals 4 is this is one of those rational functions that does simplify. So I have a graph of it for your information, and there's that hole at x equals 4. So what we're saying is we want to make this function continuous, so we need to pick a y value for k that is going to plug that hole. So from the graph, which I provided, you can see, if you pay attention to the scale really closely, that that y value should be 8. So we need k equals 8. But you want to be able to do this analytically without necessarily having to look at a graph. And so basically what we want is we want to find out what is the limit of x squared minus 16 over x minus 4 as x approaches 4. So we want k to be equal to the limit as x approaches 4 of x squared minus 16 over x minus 4. Now, you guys can see, though, that if you plug 4 in there, we end up getting 0 over 0, which means we need another method. And the other method that we know, and hopefully you recognize could work here, is that we can factor the top and bottom. So I'm going to factor to x minus 4, x plus 4, all over x minus 4, which cancels. And so now I'm going to be looking at the limit of just x approaches 4 of x plus 4. Notice I'm carrying that limit notation. And now I can plug in 4. And that gives me 4 plus 4, or 8 for my answer. So basically what I want to see here again is I need k to be the limit of that top function. And so I used my limit process and got that that was 8. And so now we know that k is going to be 8.
The last thing we're going to talk about is continuity at the endpoints of functions. Not all functions have them, but some, like the square root function that I've tried to draw here, do. And so a natural question to ask is, like, what's going on at the endpoint? Because it seems like it would be weird to say that the function isn't continuous there. But as we know, there's only a limit coming in from one side, not at the other. And so that seems like it violates the definition. For endpoints specifically, there is a little bit of a variation on the definition, which just says that as long as the appropriate one-sided limit exists, and that is the same as the function value, it's considered continuous. So to see what I mean, I drew like two things that you can compare. At the endpoint of the square root function, we would consider that continuous because the limit that's coming in from the right side at that endpoint is the same as the function value. But in contrast, the piecewise function that I have on the right side, if you look all the way to the right at that endpoint, in this case, it would be the limit from the left. The limit from the left is approaching a hole, and then the function value is at a different place. We would say that is not continuous. So at endpoints, it's enough for just the appropriate one-sided limit to be equal to the function value, and then we would say that that's continuous. And that's what you need to know about the definition of continuity at a point.